Hi, we're back again with another video. So I wanted to discuss with you guys types of selection. So when we're talking about natural selection and how nature chooses these traits, right? Chooses these traits. What I mean by it chooses the traits is that it puts on something called a selective pressure. And that can be lots of things. That's environmental, or it can be a disease of some kind. So let's discuss. So these are populations. So let's look at this first one and just focus on the first one. Okay. So on this first one, this is what we call a bell curve, and the bell curve is a traditional distribution of data. And so when we're looking at populations, it's pretty typical prior to a selective pressure. And so what you're seeing is you're seeing the number of individuals with the trait, and then you're seeing the types of traits represented. So in this case, this is about snails and their shell color. So we range from very, very light to sort of a medium brown and for the snails. And it looks like the largest amount have a neutral middle average color. So we're looking at this sort of medium beige, and that is the highest percentage of snails, the largest number of individuals. So that means that the fewest individuals have very, very light shell colors, and equally so, very, very dark shell colors. All right, so let's say that there are selective pressures going on. Let's look at this first one down here to the left. What you're going to see is something called stabilizing selection. Now, stabilizing selection chooses the middle. It says being average is best. Being middle of the road is the most successful. In real life, where do you see this? Well, you actually see this in size. So, particularly dogs. Let's see if I can get my dog. Toonie, come here. Come here. Can you come say hi? Come here, baby. Can you see her? Here. Look. Toonie, can you say hi? Come here. Hi. Hi. So this is Petunia, and she is my English Mastiff. She's so sweet. You're so sweet. But as you know, English Mastiffs are very, very large breeds, and so as such, they do not live terribly long, terribly long. No, they don't. You want to be part of it? So they do not live terribly long. So we're looking at an average life expectancy of about 10 years. Now, likewise, with really, really small dogs, like all these teacup varieties that we keep breeding, they also will not live very long. So maybe 10 years. And so part of that is because their organs wear out. Where'd you go? Their organs wear out. And so their joints also wear out. They're prone to arthritis, hip dysplasia, and organ failure. Sometimes in the smaller varieties, they are prone to many more bone injuries just simply from jumping off things because their little bones are so, so small. So also heart failure. Anyway, that's a selective pressure that says being average size is best. It makes you live longer. What doesn't make you live longer? You live longer if you have an average size. So that's stabilizing selection. So it culls the extremes. So it gets rid of the small and it gets rid of the extra, extra large. You comment? And so in this case, we're looking at the snails. So something has occurred that would require this average beige, so maybe the type of sand that is present, which means that if you have very, very light shell colors and very, very dark shell colors, you're going to be able to be seen. And that means you're going to be eaten by predators. So in this case, it pays to be average. Likewise, for dog life expectancy, it also pays to be average size. All right, directional selection. So this is where you take the same bell curve and it doesn't really change. You just shift it one direction or the other. So in this example, it's being shifted towards the darker snail, where now the highest frequency snails have more of an in-between, but a darker brown than they had before. This is seen anytime that there's a volcanic eruption because it covers the ground in this really dark rock. And so if your ground is all of a sudden a predominant black surface, then you're going to want to be as dark as possible. Okay, so in real life, another place where we see this is in giraffe necks. So something that a lot of people don't know about giraffe necks is that they do vary in length. And we have found skeletons of giraffes with short necks. And yes, it does look incredibly awkward. So we have found what we consider short necks, medium necks, and long neck giraffes. As you know, at this time, we really only have long neck giraffes around. So let's talk about why that is. Well, they still vary. Even now, we have long as the highest frequency, but we also have the ones that have extremely long necks, and ones that have more of a medium type neck still exist in the gene pool, but we just don't see them as frequently. Do you want to say hi? Do you say hi? Drop my microphone. So anyway, so what has happened? Why did that occur? What selective pressure led to that? Well, what led to that are the fires that exist in the savanna. So these trees, something that you don't know, a random knowledge time about trees in the savanna, is that a lot of them have evolved to have fireproof bark, which is amazing. So that means that the outside bark of the tree is actually fireproof. And there's so many fires there. What's causing those? Usually lightning. Lightning is causing those. And so the grass is so dry that if lightning just sparks, right? Massive fires. That was also seen in Australia. I believe part of Australia burned for there was a fire present in Australia for over 200 days. So anyway, so back to the savanna. So these giraffes, the deal is that these trees, all their food, especially because of the fires, has to be up really, really high where the fires from the grass fires cannot reach it. And so because of that fireproof bark, it's not exactly climbing up the tree that way. So these leaves have to exist just above these massive fires from the tall grass. And so the leaves and the food sources for the giraffes are up really, really high. So what does that mean? Well, it means sadly that the giraffes with short necks and some of the giraffes with medium necks starved to death because they literally could not reach the leaves for food. There was no food source for them. And so they starved. And if you are not around to reproduce, your genes don't get passed on. So that means that long neck giraffes, they were around to reproduce. And so their genes got passed on. And so now we've seen this big directional shift towards long neck giraffes where all I've ever known are long neck giraffes. But if you look in the gene pool, there's still some variation. It's just not what it used to be, right? Because if there are still these really short neck giraffes, they're still going to die. They're still not going to reproduce. And so those are going to just continually get removed from the gene pool. So now our new average is really, really long for giraffe necks. All right, so that's called directional selection. In some cases, like in ice ages, it's shifted the other way to where small is better. And so that was true of mammals. Most mammals that survived the ice age weighed under 40 pounds. And so really, really small ones survived the best. That's not to say that mammoths and stuff like that didn't make it, but they had to have really specific adaptations to make that possible. Okay. So this one is a type of selection that favors the extremes. There's another term for it. So there's stabilizing, directional, and I'm going blank on another name. This one has another name. Let me see if I can find it real fast. Oh, I found it. It's called disruptive. So I've never heard it called diversifying selection. I've always called it disruptive selection because it really disrupts everything that's going on. So on your test, it'll probably be called disruptive selection. So maybe just make a special note that it's called disruptive. Okay, so it shows you the original population here of the snails. And then something has occurred that favors the light and the dark, but not the middle. And this is a particular scenario because in normal scenarios, you can kind of favor, one or the other. Um, But in this case, it's the light and the dark. So, a place where I have seen this is in the desert. There was a volcanic eruption in the desert, but it didn't cover all of the desert sand. And so, what happened is the light colored mice survived, but also the dark colored mice could survive on the lava that had dried. And so the medium colored mice showed up on the light sand and they also showed up on the really dark rock. And so they were eaten first, which is interesting. Now, this only works if the white mice or the light tan mice, I think, if they stayed on the sand when they moved to the lava flow, they did get eaten by predators. So they sort of figured out where they blended in the best. Likewise, if the dark mice, if they moved to the light sand, they were going to get eaten. And so they learned to stay on top of the rocks for the majority of the time. So, where's another scenario in real life that this could happen besides the little snails? This happens in the Galapagos sometimes. And so the deal is that it's with the finches. They call them Darwinian finches, but they're just finches. And their beaks change um, to get different food sources. And so some of the food sources are these like these big sort of walnut looking things. And so these larger nuts that they have to crack require a beak that's shaped kind of like pliers. And so um, it really has to crack. And so it works like a nutcracker to crack open the shells. Now, the other food source that's prevalent on that island um, are really, really narrow flowers. So the opening's not very big, and the nectar is like way down in there. And so they have to have really long, skinny beaks to get back in there. They call them like needle nose plier beaks. Ding, ding, ding. And so in that case, it pays to have a really long, skinny beak or a really small, narrow beak. And in this case, it pays to have a really like dense, wide beak, right? And so the average beaks, well, they're not strong enough to crack open the nuts, but they're also not small enough to fit in and get that nectar. And so in that case, that's a disruptive selection example in real life as well. Okay, so I just wanted to explain that to you. That should be our last new material on this exam. I hope this was helpful. Junie, do you want to come say bye? You want to say bye? Here. Say bye. Bye. Bye.